Hello, in this video we are going to see how we can simulate a folded dipole antenna using CST. So in our previous video we have seen that what are the characteristics of a folded dipole antenna, what is its input impedance and all. So the input impedance of the folded dipole antenna depends upon the number of conductors or the dipoles that is connected here. So in this case you can see that it these type of dipoles consist of two dipole elements, so the total impedance is around 300 ohm. And here our aim is to design a dipole antenna at 2.45 gigahertz. So the wavelength corresponding to that frequency is 122 ohm. And as these conductors have a length of half wavelength, we can calculate the length using these equations. We are using some factorization 0.95 here because there will be some fringing effect, and because of that the length will be getting extended. So the actual length of dipole antenna will be always less than lambda by 2. Here I am going to consider the radius of wire as 1 mm and the feed gap, this gap between the elements, as 4 mm, and the gap between the elements, gap between these dipoles, as 10 mm, and this distance from the end of here to this curved as 5 mm. So it is it is always better to design, means use the length slightly less than this value, because of these curvature also, this curvature also come into the effect of radiation. So the length, it is always better to use the length less than this value. But in my case I'm not going to optimize this value, I am going to just use this. So if we simulate with this length, it is like we will be getting some frequency less than 2.45 gigahertz. So that is one of the things considered here. So let's see how we can simulate this antenna using the CST. Okay, let's start. New template, microwave and RF antennas, then wire antenna, time domain solver. All the units are okay. Then frequency from 1 to 5. I'm not going to set these field monitors. We can set after checking the results. Then click next, finish. So what I'm going to do is I'm going to draw this dipole first and then translate that dipole to at S distance. So let's do that first. So the length of the dipole is around 57.95. So let's start doing that. So for that, put the cylinder. If you click escape, it will show the dialog box, and the radius is R1. Is that minimum is L by 2 to L by 2. L is the half wavelength. So R1 I am going to consider here as 1 mm and L is 57.95. You can select little bit less value than this thing because it with this value we may be getting resonance at frequency which is less than 2.45 gigahertz. So let's see. So I have the dipole, first dipole here. So my second step is I have to translate that into S distance. So for that we can select this one, then transform, translate, copy. So in this direction I have to move, that is S. S is around 10. Okay, so we have two dipoles now. I'm just going to rename it as dipole 2. Oh, sorry, rename. I was trying to rename it as dipole 2. So we have two dipoles now. And my next step is to provide the feed here. So for that I can again go for the solid, and this is the feed. So for that also the radius is R1 and x sender y sender 0, and Z minimum is feed width. So feed width is minus f by 2 to f by 2. So actually I'm going to model this thing which has a feed gap of 4 mm. Okay, PC, then preview, f is 4 mm. Okay, so now we have created that thing here. Click OK. So my next step is I have to subtract this thing because we need a gap here. So I have to subtract that from the feed. So you can go to the modeling and use the subtract. Then it will be creating this gap here. So now we have the two dipoles, and our next step is to create these bends. So for that what we can do is, what I'm going to do is, I'll be creating some part here and I will put some loft from here to here. So that I'm going to do now. So we can see that the distance from here to here, that is the offset, is considered as around 5 mm. And if I have to create this, it has to be at a distance of s by 2. So let's first create this small portion here, and we can use some loft option. So let's go for that. So now I have to create some portion here. Okay, so let's see that. So again click on the cylinder, and this is going to be our bended portion. So I'm going to give a test bended, and it also has the radius of R1. And okay, so its orientation has to be along the x. So I have to create the cylinder along x orientation. So I have to put the orientation as x. You can see it here because my cylinder has to be oriented along the x-axis. And y sender, so here this the top portion is the y, so it has to be 0, and z sender, so here you can see that up to here it is L by 2. So I'm going to give it as L by 2 plus our offset, and x minimum and x maximum. So I'm going to create it here. So the distance of separation between these two is s by 2. Sorry, s. So I'm going to take the value in the mid, that is s by 2. So I'm going to give it a small dimension like s by 2 minus 0.2, and sorry, s by 2 plus 0.2. So why I have chosen s by 2 is I have to select the center point because the distance of separation between these two is s. That is why this thing. So if I, so what we have, offset is 5. So offset is the distance from here to here. That is I have taken as 5. So here you can see that we have created a very small cylinder having the dimension of 0.4 mm here. So I'm going to click OK. So here you can see that we have a cylinder having the same radius as this thing. So what we have to do is, now we have to do, so now we have this thing here, so we have to connect this portion to this portion. For that we can use the option loft. Okay, so for that what we have to do is we have to select the face. If you click the F, it will select the face, and this thing. Okay. So this is okay. So this is the loft option. Here you can see this is the loft option, and I'm going to create the loft. So here you can see that now it is getting connected. So this is some factor which will defines how much bend is it's offering. So if it is like high value, here you can see that it is like a 90-degree bending. So we have to put some low value for it to have a smooth bending. So maybe we can provide smooth bending like 118 or 16. So now we have a smooth bending here. Okay, so now we have the bend. So for this purpose, we have to use this function, loft function. So we have two dipoles now and bended portion and this one. This is the bend. Okay, so I'm going to rename it as, because this is also part of the bend, right? Bended 2. So what I have to do now is I have to create a mirror image of here with respect to this line. So I'm going to create the mirror. So for that you can check the transform option, then mirror, because as I need this here, you can click for copy. Okay, oh sorry. So now I have to provide which with respect to which plane I have to make it as flipping. So first one is which is the normal. So as it is along the x-axis, the normal is along x. So here you can see that it will be shifted with respect to x-axis. So as my center is here, that is s by 2, I have to give that value there, s by 2. So here you can see that it is bended, sorry, mirror transferred with respect to that point. So this is how you can do the mirroring. So now I have everything together. So now what we have to do is we have to use again mirroring with respect to this plane, that is with respect to z plane, to have this bend along here. So again go for transform. As I need this position point, this bend here, just click copy and one. Okay, so I have to mirror. Okay, so Z, because Z is along this axis, we have to mirror along the Z and we have to mirror along the origin position. So here you can see that the bend is also created here, mirrored there. So we have the complete dipole here, folded dipole here. This is how we are creating the folded dipole. Our next step is to provide the port. So to provide the port, what you have to do is you have to select the face center. So for that you can use the option pick face center C. So you can click this thing. So now I selected the face center of that, and using the option C you can select the face center. So now we have to define the port in between. So okay, so now we have to create a discrete port in between them. Okay, so we have seen that input impedance of this folded dipole is around 300 ohm. You have to use that impedance there because the impedance of this not antenna is not 50 ohm. The impedance of this antenna is not 73 ohm as that of half wave dipole. Its impedance is 300 ohm. So you have to use that impedance 300 ohm here. and click OK. So now we have the complete setup. Everything is ready. In simulation, you can check the frequency and the background. You can make sure that the material is normal. The box is um, filled with material having epsilon and mu 1, that is like a vacuum. And then boundaries, you have to make sure that open boundary is lambda by 4. And you can go to the global properties, and if you need better results, you can always increase this mesh settings. Here I'm not going to do that. And then you can check the settings here. You don't have to normalize these impedance or nothing. You can start the simulation. Okay, the simulation is complete now. Let's check the S parameter. Here you can see that it's matched at around 2 gigahertz. So if you want to have the frequency at 2.4 gigahertz, it is better to have the length optimized. I'm not going to do that now. I'm just going to check the frequency, because we need to check the electric field and magnetic field at this frequency. So here 1.97. So we are going to check the field monitors. 1.9. Okay, so maybe we can use the structure bounding box, because we don't need to simulate the electric field for the entire box. We can use the structure bounding box like this. Only the electric field around this structure is required. You can do that. And each field also like that. And far field, for the far field, we have to consider the entire domain. Okay, so now we have the E field, H field, and far field. Then start simulation. Okay, so let's check the results like far field. So you can see that it's omnidirectional, because it is like a pattern like that. So we can show the structure, and maybe far field, make the far field transparent. You can see that the field is similar to the half wave dipole. You can see the nulls are occurring along these directions, and it has a uniform pattern along this axis. So that is why we are saying it has an omnidirectional pattern. And as this is a wire antenna, if we check the directivity and the gain, there won't be much difference, because there is no dielectric loss and all here. So the directivity here is 2.79. And if you check the gain, you can see that it is also similar, 2.8. So there is no much difference here. Next thing we have to check is that matrix. You can see the impedance. Here you can see that the impedance at the resonance frequency is 300 ohm. Okay, next we have to we have to check these 2D and 3D results. So let's check the surface current. Okay, I'm not sure why it is causing the problem. Let's check. Okay, I reopened the files, and we have the electric field. Here you can see that how the electric field is showing. You can, if you want to see using the arrows, you can use the arrow option. So this is how the electric field distribution is happening here. You can see that the maximum is around the feed point, and you can see that how it is varying. So maybe we can use for the contour, so which is very easy to visualize. Here you can see that how the half wavelength distribution is happening. You can see the distribution along the dipoles. So let's see how the surface current is. So here you can see that the surface current maximum occurs here and it is going to be minimum at the ends. So this is the surface current distribution. So I hope you get some idea about how you can simulate a folded dipole and how you can visualize the electric field and magnetic field distributions. Thank you.